For more than 100 years, one single metal has quietly kept the entire modern world running. And right now, engineers in China are working on something that could finally push it aside. Stay with me to the end of this video, because what's happening here could reshape how every single AI data center on the planet gets built. And if topics like this interest you, go ahead and subscribe now, because we break down stories exactly like this one every single day. Most people never think twice about this particular material. It sits inside the walls of your house, inside your phone charger, inside the cables running underneath entire cities, and inside the massive server farms quietly powering every AI chatbot you've ever used. It has been so reliable for so long that it basically became invisible. Nobody questions the wiring in their walls, the same way nobody questions the air they breathe. But that quiet, invisible reliability is exactly what makes this story so surprising. Because the one thing capable of forcing a change to a material, this deeply embedded in modern life, turns out to be artificial intelligence itself. And the change appears to be arriving far faster than most people inside the industry originally expected. That metal is copper, and for well over a century it has powered essentially everything electrical. Every major power grid, every data center, every factory floor, and nearly every computer ever built has relied on copper wiring to move electricity, and eventually information from one place to another. Copper became so deeply embedded in modern life that most people never even stopped to think about it. It was simply the material everything else depended on, quietly doing its job in the background. But right now, something genuinely unexpected is happening. As artificial intelligence keeps growing at an almost unbelievable pace, the very technology that carried us into the digital age is starting to show real limits. Modern AI systems have become so powerful that moving data between thousands of individual processors has turned into a challenge almost as difficult as actually performing the calculations themselves. Inside many of the world's largest AI data centers today, expensive chips are sitting there waiting for information to arrive, instead of actually processing anything. The processors themselves keep getting faster every single year, but the connections linking them together are struggling to keep pace. That mismatch has created one of the single biggest engineering challenges of this entire AI era, and researchers and technology companies all over the world are now racing to solve it. One country in particular has been announcing an unusually large number of breakthroughs specifically in this area, China. Over the past few years, Chinese researchers have revealed advances in optical networking, air-filled fiber technology, glass-based communication systems, photonic chips, and remarkably fast data transmission methods. On their own, each individual announcement might seem like a fairly small, unrelated story, but taken together, they point toward something much bigger. Instead of simply asking how to make copper slightly better, these researchers appear to be asking a completely different question entirely. What if the future of computing doesn't actually need copper at all? I know that probably sounds almost impossible to believe. Copper has stood as one of civilization's single most important industrial materials for generations now. You'll find it in power plants, inside smartphones, running through electric vehicles, and threaded through internet cables everywhere you look. Replacing it on any meaningful scale would mean fundamentally rethinking some of the most important technologies humanity currently relies on. And yet, artificial intelligence may genuinely be forcing exactly that kind of transformation to happen, faster than almost anyone expected just a few years ago. So why exactly is copper becoming such a bottleneck? The underlying reason is actually fairly simple once you break it down. Artificial intelligence doesn't just need faster individual processors, it needs all of those processors to communicate with one another almost instantly. Picture trying to hold a single conversation with 10,000 people at the exact same time. Even if every single person involved could think incredibly quickly, the overall discussion would still slow to a crawl if messages couldn't travel quickly enough between everyone involved. Something remarkably similar happens inside modern AI supercomputers. These systems can contain thousands, sometimes even tens of thousands, of advanced processors, all working together as one single enormous machine. Every second, those processors are exchanging absolutely massive amounts of information with each other. If the underlying communication network can't keep up with that pace, the entire system becomes noticeably less efficient, no matter how powerful the individual chips happen to be. For years now, engineers have been steadily improving copper cables, making them faster, reducing electrical interference, and designing increasingly advanced connection technologies to squeeze more performance out of the material. But every single improvement also seems to introduce a brand new challenge right alongside it. Electrical signals naturally generate heat as they travel. Higher transmission speeds consume noticeably more power. Longer cable distances weaken the signal, requiring extra equipment along the way just to restore that signal before the information can continue traveling onward. As AI systems keep growing larger and larger, all of these individual problems start compounding on top of each other. That's precisely why a growing number of engineers now believe the next major leap forward won't come purely from building faster processors. It will come instead from fundamentally changing the way data actually moves between them. Instead of relying entirely on electricity flowing through copper wiring, future computing systems may increasingly send information as pulses of light instead. Unlike ordinary electrical signals, light can travel enormous distances while losing remarkably little of its original signal strength along the way. Optical communication also generates considerably less heat, and it can carry significantly more information at the exact same time compared to traditional copper. For decades now, fiber optic cables have already been connecting cities and entire continents together using light instead of electricity. What researchers are working toward now is bringing that same basic concept directly inside AI computers themselves. Rather than connecting individual processors using copper traces and electrical cables, the way computers have always been built, future AI systems could increasingly rely on optical connections that move information using particles of light instead of the flow of electrons. That particular idea has become one of the hottest areas of research anywhere in modern computing today. And this is exactly where China's recent string of announcements starts to make a lot more sense when you look at them together. Over the past several years, Chinese universities, telecommunications companies, and semiconductor researchers have repeatedly demonstrated new technologies built around optical communication. Some of these projects focused specifically on photonic processors. Others explored glass-based chip designs entirely. Some managed to demonstrate record-breaking fiber transmission speeds, while still others introduced completely new networking techniques designed specifically for the unique demands of artificial intelligence workloads. Just this year, Chinese optical communication companies showcased some genuinely striking breakthroughs at major international technology conferences. One leading Chinese fiber optic manufacturer demonstrated a new kind of hollow core fiber, a fundamentally different design where light travels mostly through air rather than through solid glass. Because light naturally moves faster through air than it does through glass, this approach can cut transmission latency by roughly a third compared to traditional fiber optic cables, while also offering a genuinely enormous amount of potential bandwidth, reportedly exceeding 200 terahertz. Separately, a partnership between a major Chinese telecom carrier and other domestic technology companies managed to demonstrate transmission speeds of around 2 terabits per second over a single wavelength of light, adding up to more than 100 terabits of total capacity across a 20-kilometer stretch of this new hollow core fiber. To put those numbers into more everyday terms, a single wavelength of light carrying 2 terabits per second could theoretically transfer the entire contents of several hundred high-definition movies in less than a second. And that's just one single wavelength traveling down one single strand of fiber. Multiply that across the many separate wavelengths these systems can carry simultaneously, and you start to get a sense of just how much raw capacity engineers are now working with. Several major Chinese fiber and telecommunications companies showcased this kind of hollow core fiber technology together at a large international technology conference earlier this year, presenting it alongside broader AI computing infrastructure solutions built specifically to support these kinds of massive data transfer speeds inside modern data centers. While the specific technical details differ from one project to the next, the overall underlying direction remains remarkably consistent across all of them. Move more information, use less energy, generate less heat, and eliminate bottlenecks wherever they show up. If these particular technologies continue improving at their current pace, they could end up reshaping far more than just the inside of data centers. Modern artificial intelligence already touches healthcare, autonomous vehicles, robotics, scientific research, financial systems, manufacturing, logistics, and national infrastructure all at once. Every meaningful improvement in overall computing efficiency creates ripple effects that spread throughout the entire global economy. That's exactly why replacing even a portion of today's copper-based infrastructure would represent far more than a simple engineering milestone. It would represent a genuinely fundamental shift in how computers themselves get designed and built from the ground up. Of course, none of this means copper is somehow about to disappear tomorrow. It remains one of the most reliable, affordable, and widely used industrial materials found anywhere on Earth. Millions of miles of existing electrical wiring simply cannot be replaced overnight, no matter how promising a new technology looks on paper. But history has shown us again and again that foundational technologies tend to remain dominant right up until a new generation quietly becomes good enough to solve problems the older technology was simply never designed to handle in the first place. Steam power eventually gave way to electricity. Vacuum tubes eventually gave way to transistors. Traditional hard drives began sharing space with flash memory as storage technology matured. Each one of those earlier transitions took years, sometimes decades, to fully play out, and in every single case, the older technology kept right on working reliably in plenty of applications long after the newer replacement had already started taking over the most demanding use cases. And now, some engineers genuinely believe another major transition may already be quietly getting underway. Not because copper suddenly became a bad material overnight, but because artificial intelligence has created a set of demands that copper was simply never originally designed to meet. To really understand why so many researchers around the world are looking beyond copper right now, it helps to understand just how dramatically artificial intelligence has changed the underlying demands placed on modern computing infrastructure. Only a handful of years ago, the world's largest data centers were designed primarily to handle cloud storage, video streaming, everyday web applications, and general online services. Those particular workloads certainly required fast, capable hardware, but they were also relatively predictable in nature. Servers processed individual requests, sent back responses, and simply repeated that basic cycle millions of times every single day without much variation. Artificial intelligence changed those underlying rules almost completely. Training a modern AI model requires thousands of processors working together as a single unified machine. Every one of those individual processors is constantly exchanging enormous amounts of information with every other processor across the entire system. Rather than sending occasional bursts of data the way older systems did, these AI networks operate almost continuously, moving information back and forth at genuinely incredible speeds around the clock. At this point, the real challenge isn't actually performing the underlying calculations anymore. The challenge has shifted entirely toward simply delivering the necessary data fast enough to keep every processor properly fed with information. Picture building the fastest sports car ever engineered, and then forcing it to drive through heavy city traffic every single day. No matter how powerful that engine happens to be, the surrounding traffic ultimately limits how well the car can actually perform in practice. That's essentially the exact situation happening inside many modern AI computing clusters today. Individual processors can complete their calculations at genuinely astonishing speeds. But if those same processors are constantly forced to wait around for data to arrive, all of that expensive computing power simply sits idle instead of doing useful work. Even a tiny individual delay becomes genuinely significant once you multiply it across thousands of processors all working simultaneously. Think about it a different way too, like an orchestra made up of 10,000 individual musicians. Even if every single musician involved happens to be exceptionally talented on their own instrument, the overall performance still falls apart completely if they can't hear the conductor clearly, or stay properly synchronized with everyone else playing around them. In music, timing ends up mattering just as much as raw individual skill. Large AI computing clusters operate in a remarkably similar way. Every single processor performs its own calculations independently, but all of those processors must constantly exchange information with the rest of the system to stay properly synchronized. If that synchronization ever slows down even slightly, overall system performance can drop dramatically as a result. This is exactly why engineers have increasingly started describing modern AI infrastructure as fundamentally a communication problem, rather than simply a computing problem in the traditional sense. Engineers often describe this particular situation as a communication bottleneck, and it's one of the biggest reasons why building larger and larger AI systems keeps becoming more and more expensive over time. Simply adding more processors to a system doesn't automatically produce a proportional gain in overall performance. As these systems continue growing in size, the communication happening between all those individual processors becomes considerably more complicated to manage. More hardware naturally means more cables. More cables tend to mean more electrical interference. Higher data transmission rates generate additional heat as a side effect, and more heat, in turn, requires larger, more expensive cooling systems, which drives up both electricity consumption and overall operating costs. Eventually, engineers reach a genuine turning point where simply improving the processors alone no longer delivers the performance gains everyone expects. At that stage, the surrounding network itself effectively becomes the true limiting factor holding the whole system back. This is exactly where optical communication really starts to stand out from the alternatives. Unlike traditional copper connections that transmit ordinary electrical signals, optical systems instead use carefully timed pulses of light, traveling through glass fibers or specially designed photonic pathways. Light offers several genuinely important advantages in this particular context. First, it can carry significantly larger amounts of information across long distances while losing only a minimal amount of signal strength along the way. Second, optical communication produces far less electrical interference compared to copper, which makes it considerably easier to maintain consistent signal quality even as overall bandwidth demands keep increasing. Third, because light doesn't generate electrical resistance in anything close to the same way copper conductors do, many optical systems can meaningfully improve overall energy efficiency, especially when it comes to moving truly vast amounts of information between different computing clusters. These particular advantages become increasingly valuable as AI infrastructure keeps expanding at its current breakneck pace. And this helps explain exactly why recent announcements coming out of China have attracted so much international attention. Rather than focusing purely on designing ever faster individual processors, Chinese researchers have repeatedly introduced entire technologies specifically aimed at improving how information itself actually moves through a system. Some projects have explored advanced photonic chips capable of handling optical signals directly without needing to constantly convert back and forth into electrical signals along the way. Others have focused specifically on developing ultra-low-loss optical fibers capable of transmitting enormous amounts of information across genuinely impressive distances. Several different research groups have also demonstrated new forms of integrated optical networking designed specifically to handle the unique demands of artificial intelligence workloads. Although these individual projects differ quite a bit in their specific technical approach, they all seem to be pursuing essentially the same underlying objective: removing communication bottlenecks before they become the single biggest obstacle standing in the way of continued AI progress. One particularly interesting direction within this broader trend involves bringing optical communication much closer to the actual processors themselves, rather than keeping it confined to the connections between separate buildings or data centers. Today, optical fibers already connect entire buildings, cities, and even continents together across the globe. Inside individual computers, however, electrical copper traces still handle the overwhelming majority of communication between processors, memory, and networking hardware. Future computing systems may increasingly blur that particular distinction. Instead of constantly converting information back and forth between electrical and optical signals multiple separate times, researchers are actively hoping to move light much deeper into the core of computing systems themselves. Some longer-term visions even imagine optical communication eventually operating directly between individual processors inside the most advanced AI servers. While that particular future remains firmly under active development rather than being fully realized today, progress in this specific area is accelerating at a genuinely remarkable pace. It's worth pointing out, though, that this transition isn't happening in isolation, and it isn't purely a China story either. At major international optical communication conferences held earlier this year, companies from around the world, including several based in the United States, presented their own competing approaches for bringing optical technology closer to AI processors. Some of these companies have been showcasing what's known as co-packaged optics, essentially integrating optical components directly into chip packaging itself, rather than relying on separate removable optical modules. One major social media company recently shared detailed reliability data suggesting this particular approach can actually outperform older-style pluggable optical transceivers in real-world deployment. Industry analysts covering these conferences have generally suggested that within the next 5 years or so, most high-bandwidth connections throughout AI data centers could shift towards some form of optical technology. That said, most experts covering this space don't expect a complete total replacement of copper. Instead, the more likely outcome seems to be what industry analysts have started calling interconnect heterogeneity, meaning multiple different technologies, copper and optical alike, coexisting together and getting deployed based on whichever specific job they happen to handle best within a given system. China has invested heavily in photonics research, semiconductor manufacturing, telecommunications infrastructure, and artificial intelligence development over the past decade or so. These substantial investments have created an entire ecosystem where universities, state research laboratories, private technology companies, and manufacturing firms frequently work on complementary pieces of the exact same overarching technological challenge. One research team develops improved optical materials. Another team focuses on refining photonic chip designs. A separate team works on designing better networking equipment. Yet another team optimizes the AI software needed to properly take advantage of faster underlying communication. Together, all of these individual advances create a kind of cumulative momentum that no single isolated breakthrough could ever fully explain on its own. This also helps explain why so many of these recent headlines seem to connect together once you look closely. Glass-based AI chips, photonic processors, air-filled fiber, optical networking, high-speed AI interconnects. These aren't really isolated inventions competing directly against one another for attention. They're actually different pieces of one much larger, interconnected puzzle. If enough of these individual pieces successfully come together, future AI systems could end up looking fundamentally different from today's existing computer architectures. Instead of relying primarily on electrical pathways built entirely around copper, much of the underlying communication layer inside these systems could gradually shift toward optical technologies instead. That doesn't necessarily mean copper gets eliminated completely from the picture. Power delivery throughout these systems will still require traditional electrical conductors for the foreseeable future. Many electronic components will also continue depending on conventional circuit designs for years to come, but the specific role copper plays in moving enormous quantities of digital information around may genuinely begin shifting in a meaningful way. That particular possibility carries significant implications that extend well beyond pure engineering considerations. Data centers already consume absolutely enormous amounts of electricity, and artificial intelligence keeps pushing that demand higher with each passing year. According to recent industry estimates, hyperscale cloud providers are expected to spend somewhere around $760 billion on data centers and broader AI infrastructure this year alone, representing a genuinely dramatic acceleration compared to prior years, with total spending up roughly 70% compared to the year before. A substantial share of that spending, somewhere around $450 billion, is being directed specifically toward AI infrastructure. If faster optical communication genuinely allows these AI systems to accomplish more actual work while consuming less overall energy in the process, the resulting economic impact could end up being genuinely substantial. Lower operating costs, reduced cooling requirements, higher overall computing efficiency, and considerably better scalability as these systems continue growing larger over time. These particular benefits matter well beyond just technology companies themselves. Healthcare researchers could potentially analyze much larger medical data sets, spotting patterns across millions of patient records that would be genuinely impossible to process using older, slower infrastructure. Climate scientists could run considerably more detailed simulations of complex environmental systems, modeling weather patterns and long-term climate shifts with a level of precision that simply wasn't practical before. Manufacturers could optimize their production lines using increasingly sophisticated AI systems, catching defects and inefficiencies in real time rather than after the fact. Financial institutions could process significantly larger volumes of information in real time, spotting fraud or market shifts the moment they start happening rather than hours later. Autonomous vehicle developers could improve their decision-making capabilities through access to more powerful underlying training infrastructure, ultimately making self-driving systems safer and more reliable. The resulting ripple effects genuinely become enormous once you start tracing them all the way through different industries, touching areas of daily life that, on the surface, have nothing to do with data centers or fiber optic cables at all. This is one of the main reasons governments around the world have increasingly started treating artificial intelligence as a form of strategic national infrastructure, rather than simply viewing it as another ordinary software industry. Countries are now investing not just in AI models themselves, but also in the underlying factories, supply chains, communication systems, and semiconductor technologies genuinely required to sustain long-term progress in this space. China has been particularly active in pursuing exactly this kind of broad, systems-level approach. Its investments span semiconductor manufacturing, optical communications, telecommunications equipment, artificial intelligence research, advanced materials, science, and industrial automation all at once. Whether every single individual project within this broader push ultimately succeeds remains genuinely uncertain, since research of this kind always involves a fair number of setbacks along the way. Not every promising breakthrough manages to reach actual commercial production. Some technologies require years of additional refinement before becoming economically practical at real-world scale. Others may simply never make it out of the laboratory setting at all, but the overall underlying direction is becoming increasingly clear regardless of these individual uncertainties. The broader industry is actively preparing for an era where moving information efficiently becomes just as important as actually processing it in the first place. And that's precisely where optical technologies could genuinely end up reshaping the entire landscape going forward. So, does any of this actually mean copper is finished for good? Not even close, honestly. Despite all the genuine excitement currently surrounding photonic communication and optical networking, copper remains one of the single most important engineering materials ever discovered by humanity. It's affordable, remarkably durable, highly conductive, and backed by more than a full century of accumulated manufacturing experience and infrastructure. Nearly every power grid, industrial machine, everyday consumer electronic device, and data center still depends on copper in some meaningful way, and that isn't likely to change anytime soon. The future almost certainly isn't going to be some kind of world entirely without copper. It's far more likely to end up being a world where copper and optical technologies each handle whichever specific jobs they happen to perform best. Electricity itself will likely keep flowing through copper for the foreseeable future, but the actual information riding on top of that electrical infrastructure may increasingly travel through pulses of light instead. Inside tomorrow's AI data centers, electrical power will still need to reach every processor, memory module, storage device, cooling system, and piece of networking equipment throughout the facility. And copper remains exceptionally well suited for delivering that raw power efficiently. The genuine challenge isn't really about electricity itself. The challenge has always really been about information and how quickly that information can move between an ever-growing number of processors working together. Some industry experts have started comparing this current transition to the historical process of building highways. When traffic levels were relatively light, ordinary roads worked perfectly well for everyone's needs. As cities gradually grew larger, though, those same roads became increasingly congested over time. Eventually, engineers had to respond by building multi-lane highways, bridges, tunnels, and entirely new transportation systems from scratch to keep pace with growing demand. Artificial intelligence appears to be going through a remarkably similar kind of transition right now. The processors themselves keep steadily improving year over year, but the underlying highways carrying information between all of those processors need to improve right alongside them. That's exactly why networking companies have quietly become some of the most important players across the entire AI industry, right alongside the more famous chip makers everyone already talks about. It's also why semiconductor companies increasingly describe their products in terms of entire computing platforms these days, rather than talking about individual chips in isolation the way they used to. The future of this industry increasingly belongs to complete, tightly integrated systems, ones where processors, networking memory, storage, cooling, software, and communication all work together with a genuinely extraordinary level of efficiency. China appears determined to compete seriously across every single one of those different layers at once, rather than betting everything on just one narrow piece of the puzzle. We've already seen meaningful domestic progress across memory manufacturing, advanced chip packaging, optical communication, dedicated AI accelerators, photonic research, glass-based technologies, and increasingly fast networking equipment. Each individual announcement might look independent on its own, but together they reveal a much broader and more coordinated strategy taking shape. Whether this particular transition ultimately plays out over the next 5 years or closer to 15, one thing already seems genuinely clear at this point. The ongoing global race in AI infrastructure is no longer only about who can build the single fastest chip. It's increasingly about who can build the smartest, most efficient overall system for connecting all of those chips together. Companies in the United States, Europe, Japan, South Korea, and Taiwan are all continuing to make remarkable advances of their own in this space, and the overall competition remains genuinely intense across the board. Many of today's most exciting experimental technologies will still need years of additional engineering work before they ever reach widespread, everyday commercial deployment, so it's worth staying realistic about the pace of change here, rather than assuming everything shifts overnight. Because in tomorrow's AI-powered world, the fastest individual processor won't necessarily come out on top. The processor that spends the least time waiting around for data will. And if light genuinely does end up replacing copper for many of these critical internal connections, we may well be witnessing one of the biggest infrastructure transitions in the entire history of modern computing. If you enjoyed this breakdown, make sure to like this video, subscribe to the channel, and turn on notifications so you don't miss anything going forward. We cover stories exactly like this one all the time, breaking down the biggest breakthroughs happening across AI, semiconductors, photonics, robotics, energy, and advanced manufacturing from around the world. Let me know what you think down in the comments below. Do you think optical communication will eventually replace copper inside AI systems entirely? Or do you think copper will remain the backbone of computing for decades still to come? Thanks so much for watching, and I'll see you in the next one.